By the early 20th century, physics had already learned to be cautious about stillness. Space could curve, fields could persist without particles, energy could exist without objects. Yet there remained a comforting assumption beneath all of this. If everything were removed, if motion ceased, if energy were minimized, then perfect rest should be possible. A true quiet, a final calm. Quantum mechanics quietly removed that possibility. Quantum mechanics is not a small correction to classical physics. It is a framework built to describe nature at very small scales, where atoms, electrons, and photons dominate behavior. It emerged not from philosophical preference, but from repeated experimental failures of classical ideas. Certain phenomena simply refuse to behave smoothly or continuously. One of the most important figures in shaping this framework was Werner Heisenberg. In 1927, Heisenberg articulated what became known as the uncertainty principle. This principle does not describe a limitation of instruments or technique. It describes a limitation built into nature itself. At its heart, the uncertainty principle states that certain pairs of physical quantities cannot both be known with arbitrary precision at the same time. The most famous pair is position and momentum. The more precisely the position of a particle is known, the less precisely its momentum can be known, and vice versa. This is not because measurement disturbs the system in a clumsy way. It is because particles do not possess exact values for these quantities simultaneously. The uncertainty is not something added by observation. It is something that exists before any observation takes place. This immediately challenges the idea of perfect rest. Rest implies a particle with precisely zero momentum, sitting at a perfectly defined position. Quantum mechanics forbids this combination. If a particle were perfectly localized, its momentum would become highly uncertain. If its momentum were precisely zero, its position would spread out. There is no way around this. It is not a matter of clever setup or improved equipment. It is a structural feature of the quantum world. This means that at small scales, stillness is not an available state. Motion, in some form, always remains. Even in the lowest possible energy state known as the ground state, particles retain residual motion. This is often referred to as zero-point energy. Zero-point energy does not mean that energy is arbitrarily large. It means that energy cannot be reduced to nothing. There is a minimum, a floor beneath which systems cannot descend. This is easy to overlook because everyday objects average over enormous numbers of particles. The restless motion of individual atoms cancels out at large scales. A table feels solid and still. A room feels calm. But at the microscopic level, motion persists relentlessly. This persistence has measurable consequences. Atoms do not collapse because electrons retain motion even in their lowest energy states. Molecules do not freeze into rigid structures at absolute zero. Quantum fluctuations prevent total stillness. What matters here is not the details of atomic structure, but the principle behind them. Quantum mechanics does not allow perfect rest. It replaces it with the lowest possible activity. This shifts the meaning of emptiness once again. Even if all particles were removed from a region, the quantum rules governing particles do not disappear. The framework remains, and that framework forbids complete stillness. Uncertainty in this context is not ignorance. It is not a statement about what humans know. It is a statement about what exists. A particle does not secretly have a precise position and momentum waiting to be discovered. Those quantities are genuinely indefinite until constrained by interaction. This distinction is essential. For a long time, physicists hoped that uncertainty reflected missing information. Perhaps deeper variables existed beneath quantum mechanics. Perhaps nature was deterministic after all, and uncertainty was only apparent. Experiments repeatedly ruled this out. Tests of quantum correlations, including those inspired by John Bell in the 1960s, showed that no local hidden variable theory could reproduce the observed results. Uncertainty was not a temporary placeholder. It was fundamental. This has direct consequences for emptiness. If uncertainty governs all physical systems, then empty space cannot be perfectly calm. Even the absence of particles does not exempt a region from quantum rules. At this stage, the idea of a quiet vacuum becomes suspect. Classical intuition suggests that removing particles removes activity. Quantum mechanics suggests otherwise. Activity does not require particles to be present in a persistent way. It can emerge transiently, fluctuate, and vanish again, constrained only by uncertainty. It is important to be precise here. Quantum mechanics does not say that anything can happen anywhere at any time. The uncertainty principle sets strict limits. Fluctuations are constrained. Energy must still be conserved on average. Effects are subtle, but subtle does not mean negligible. The fact that perfect rest is forbidden means that emptiness cannot be fully emptied. There is always a baseline level of activity allowed by the rules of the theory. This is deeply counterintuitive. Human experience associates quiet with absence, silence with nothing happening. But quantum mechanics replaces silence with a kind of whisper. Not loud enough to notice directly, but never completely gone. There is a gentle humour in this if one allows it. Nature seems unwilling to sit still even when given the chance. Remove everything, and it fidgets anyway. This restlessness does not announce itself dramatically. It does not create explosions or visible motion. It exists at scales far removed from everyday experience. Yet it has consequences that accumulate. The uncertainty principle also introduces a new way of thinking about limits. Classical physics often asks what happens if something is reduced to zero. Zero velocity, zero temperature, zero energy. Quantum mechanics replaces zero with minimum, the smallest allowed value, the lowest possible state. This minimum is not arbitrary. It emerges from the structure of the theory itself. It is as fundamental as conservation laws. By this point, emptiness has been transformed repeatedly. It has gained geometry, fields, and energy. Now it gains irreducible motion, a baseline activity that cannot be removed. Quantum mechanics does not yet tell us exactly what empty space does. It tells us what empty space cannot do. It cannot be perfectly still. It cannot be perfectly defined. It cannot be a silent void. This realization prepares the ground for a more explicit picture of vacuum behavior. If uncertainty forbids stillness, then even the vacuum, defined as the lowest energy state of a system, must exhibit activity. That activity is not chaos. It is structured, it follows rules, it respects limits, but it is real. The idea of nothing is now under serious pressure. Once uncertainty is accepted as fundamental, emptiness can no longer be imagined as a calm endpoint. It becomes a dynamic condition, constrained but restless. And it is within that restlessness that the vacuum begins to reveal its true character. Once quantum mechanics forbids perfect stillness, emptiness takes on a new and more precise meaning. Physicists do not abandon the idea of a vacuum, they redefine it. The vacuum becomes not the absence of everything, but the lowest possible energy state allowed by the laws of nature. This is what is meant by the quantum vacuum. In everyday language, a vacuum suggests removal. Take everything out and what remains is nothing. In quantum physics, the vacuum is not what remains after everything's removed. It is a specific state, the ground state of a system, the configuration with the least energy permitted, but not zero energy. This distinction matters. The quantum vacuum is not empty in the classical sense. It is a condition of fields rather than particles. Even when no particles are present, the fields themselves remain, and they cannot be completely still. This view comes most clearly from quantum field theory, the framework that combines quantum mechanics with the concept of fields. In quantum field theory, particles are not fundamental objects floating through space. They are excitations of underlying fields, An electron is a localized excitation of the electron field. A photon is an excitation of the electromagnetic field. The fields come first. Particles are what fields do when energy is concentrated. This idea emerged gradually in the early 20th century. One of the key figures in this transition was Paul Dirac. Dirac worked to merge quantum mechanics with special relativity, and in doing so, he helped formalize the idea that fields themselves must be quantized. Energy could not vary continuously at small scales. It came in discrete amounts. Quantizing a field means treating each mode of the field like a quantum system with allowed energy levels. Even the lowest level, the ground state, carries energy. This is not an optional feature. It arises directly from the uncertainty principle. If a field were to have exactly zero energy, its value and rate of change would both need to be precisely defined. Quantum mechanics forbids that. The field must fluctuate, even in its lowest state. This leads to a quiet but profound conclusion. Empty space, defined as a region with no particle present, is still filled with fields, and those fields, even in their ground states, fluctuate. These fluctuations are not large. They do not pile up into visible motion. They are constrained tightly by quantum rules. But they are real. This is why physicists describe the quantum vacuum as restless. Not chaotic, not violent, but never perfectly still. Energy briefly appears in one form and disappears in another, constrained by uncertainty and conservation laws. It is important to be careful here. Popular descriptions often speak of particles popping in and out of existence. This language is useful, but imprecise. What actually fluctuates are fields. The particle picture is a way of describing certain interactions, not a literal swarm of objects appearing from nothing. The vacuum, in quantum field theory, is a seething background of potential, a baseline activity that never quite shuts off. It is not empty in the sense of absence. It is empty only in the sense that no lasting excitations are present. This distinction helps avoid confusion. The quantum vacuum does not violate conservation of energy. Over time, energy remains balanced. Fluctuations are temporary and constrained. They do not allow free energy extraction or spontaneous creation of matter without cause. Yet despite these limits, the vacuum has observable consequences. The lowest energy state of a field influences how particles behave. It shifts energy levels, it modifies forces, it affects decay rates. This means the vacuum is not a passive backdrop. It participates in physical processes even when nothing appears to be happening. There is a subtle change in perspective here. Instead of asking what exists in empty space, physics asks what state the fields are in. Emptiness becomes a statement about configuration, not absence. This also explains why removing particles does not simplify the universe as much as intuition suggests. Particles are only one expression of deeper structures. Beneath them lie fields that cannot be removed without removing the framework of physics itself. The quantum vacuum is the state of those fields when they are as calm as the rules allow, and that calm still contains motion. This idea can feel unsettling because it removes the concept of absolute nothingness. There is no switch that turns reality completely off. There is always at least a hum. Yet this hum is not arbitrary. It is tightly regulated. The vacuum does not explode with energy. It does not collapse into chaos. Its fluctuations average out. Their effects are subtle, cumulative, and precise. One way to understand this is to imagine a perfectly calm lake that can never be completely flat. No matter how still the air, tiny ripples persist. They're not caused by wind or disturbance. They arise from the water itself responding to unavoidable constraints. The lake is calm, but not frozen. The quantum vacuum behaves in a similar way. It is the calmest state possible, not the quietest one imaginable. This framework resolves several earlier puzzles. Fields no longer require a classical medium. Light does not need an ether. Electromagnetic waves propagate as excitations of the electromagnetic field, which exists everywhere space-time allows. It also explains why emptiness resists being emptied. Even after removing matter, air, radiation, and heat, the underlying fields remain. Their ground states remain. Their fluctuations remain. At this point, emptiness has become something precise and technical. It is no longer a vague absence. It is a well-defined physical state with measurable properties, and yet everything described so far has remained largely theoretical. The quantum vacuum is a consequence of the mathematics. It is required for consistency. But physics demands more than internal coherence. It demands contact with observation. The natural next question is simple. If the vacuum is restless, does that restlessness do anything measurable? The answer is yes. The quantum vacuum does not merely exist as a conceptual necessity. It leaves fingerprints on the physical world. It shifts forces. It alters energy levels. It produces effects that can be detected under carefully controlled conditions. The vacuum, once redefined as the lowest energy state of quantized fields, is no longer invisible. It is subtle, but it is active. And when its activity is isolated, constrained, or shaped, it begins to reveal itself. The transition from theory to effect has already begun. Once the quantum vacuum is understood as the lowest energy state of fields, a natural question follows. If fields can never be perfectly still, what does that restlessness look like? The answer is subtle, restrained, and far less dramatic than popular imagery suggests. It is known as vacuum fluctuation. Vacuum fluctuations are not explosions in empty space. They are not storms of activity or bursts of chaos. They are small, fleeting variations in the energy of fields that occur because perfect stillness is forbidden. The vacuum is calm, but it is not frozen. In quantum field theory, every field has a ground state. That state carries a minimum amount of energy, known as zero-point energy. Because of the uncertainty principle, the field cannot settle into a single fixed value everywhere. Instead, it fluctuates slightly around its minimum. These fluctuations are constrained in both size and duration. The smaller the region of space being considered, the larger the possible fluctuations. The longer a fluctuation lasts, the smaller its energy must be. These limits are not arbitrary. They follow directly from the structure of quantum mechanics. This is why vacuum fluctuations are often described as brief and local. They occur over extremely small distances and extremely short times. At everyday scales, they average out. Nothing accumulates. Nothing builds up. One way this behavior is sometimes described involves transient particle activity. The language of particles appearing and disappearing is common, but it must be handled carefully. What fluctuates are fields. Particles are a way of describing certain interactions when energy becomes localized enough to behave as a discrete excitation. In the vacuum, fluctuations can momentarily resemble particle pairs and calculations. These are often referred to as virtual particles. They are not particles in the everyday sense. They cannot be isolated, detected directly, or stored. They are mathematical representations of temporary field excitations within interactions. The key point is not that particles pop into existence from nothing. The key point is that fields fluctuate within strict limits, and those fluctuations can influence measurable processes. Duration matters here. These fluctuations exist for extraordinarily brief intervals. They do not persist long enough to be observed as independent objects. They appear only as intermediate effects in interactions. Their influence is subtle and indirect. Scale matters just as much. Vacuum fluctuations are most significant at very small distances. As regions grow larger, the effects smooth out. At human scales, the vacuum appears quiet. At atomic and subatomic scales, it is gently restless. This balance prevents chaos. The vacuum is not unstable. It does not collapse or explode. The fluctuations are self-regulating. They are allowed precisely because they are constrained. It is tempting to imagine nothingness as a blank slate where anything might happen. Quantum mechanics does not permit this. The vacuum follows rules. Energy is conserved overall. Fluctuations are bounded. Cause and effect remain intact. This constraint is essential. Without it, the universe would be unrecognizable. The fact that vacuum fluctuations are limited is what allows matter to exist in stable forms. Atoms do not dissolve. Space does not tear itself apart. The effects of these fluctuations can be inferred through their influence on measurable quantities. They shift energy levels in atoms. They modify the strength of forces over very short distances. They alter the behavior of particles in subtle but predictable ways. One example involves the energy levels of electrons in atoms. Precise measurements reveal small shifts that cannot be explained without accounting for vacuum fluctuations. The background activity of fields slightly alters how particles interact, even when nothing seems to be happening. Another example appears in force calculations. At very small separations, the vacuum contributes corrections to the forces between charged particles. These corrections are tiny, but they are consistent and measurable. What matters is not the size of any single fluctuation, but their collective influence. Over time and across many interactions, the vacuum leaves a trace. This reinforces an important idea. Nothingness is not chaotic. It is constrained activity at the lowest possible level. The vacuum does not choose randomly what to do. It follows statistical patterns defined by the underlying theory. There is a calm regularity to this. The vacuum fluctuates the way a tightly stretched surface vibrates. Small, rapid motions that never grow out of control. The system remains stable because the rules enforce balance. It is also important to note what vacuum fluctuations are not. They are not a source of free energy. They cannot be harvested. They do not violate conservation laws. Attempts to imagine extracting usable energy from the vacuum misunderstand the nature of these effects. The vacuum does not give energy away. It responds to boundaries, constraints, and interactions. When conditions change, the vacuum adjusts. That adjustment can produce observable effects, but always within the limits imposed by physics. This is why experimental confirmation matters. Vacuum fluctuations are not accepted because they sound intriguing. They are accepted because they produce precise testable predictions. Before turning to experiments, it is worth pausing on the conceptual shift that has taken place. Emptiness has been stripped of drama. It is no longer a void where anything might happen. It is a structured state governed by rules that limit activity as much as they allow it. The vacuum is restless but disciplined, active but restrained. It does not contradict the stability of the universe. It supports it. This perspective also explains why emptiness resists simple description. It is neither a thing nor a nothing. It is a condition, a state defined by minimum energy and unavoidable fluctuation. Once this is understood, the next step becomes natural. If vacuum fluctuations influence forces and energy levels, then they should be observable under the right conditions, not by watching particles appear, but by measuring the consequences of their absence. Physics does not ask the vacuum to announce itself. It asks whether the world behaves differently because the vacuum is there. The answer, quietly and consistently, is yes. The task now is to isolate those differences, to shape emptiness in ways that reveal its structure, to move from implication to demonstration. Vacuum fluctuations prepare the ground for this transition. They explain why effects exist. Experiments reveal that they do. The calm hum of nothing is not imagined. It leaves marks, and once those marks are measured, emptiness becomes not just a theoretical necessity, but an experimental reality. At some point, theory must touch the world. Ideas about emptiness can be elegant, consistent, and mathematically necessary. But physics ultimately asks a simple question. Does any of this do something that can be measured? One of the clearest answers to that question comes from an effect that is surprisingly quiet, remarkably precise, and almost impossible to dismiss. It is known as the Casimir effect. In the late 1940s, the Dutch physicist Hendrik Casimir was studying quantum fields in confined spaces. Casimir was not looking for a philosophical statement about nothingness. He was working on practical problems related to electromagnetic forces. What emerged from that work, however, was a direct prediction about how empty space itself should behave. The setup is conceptually simple. Take two flat, uncharged metal plates, place them extremely close together, separated by a tiny gap. Remove as much air as possible so that the space between them is effectively a vacuum. According to classical physics, nothing interesting should happen. No charge, no force, just two neutral objects sitting quietly in empty space. Quantum physics predicts something else. The electromagnetic field exists everywhere, including inside that gap. Even in its lowest energy state, the field fluctuates, but those fluctuations are not arbitrary. They depend on the boundaries of the space they occupy. Only certain field modes are allowed to exist between the plates, while others are excluded. Outside the plates, the field has more freedom. More modes are allowed. The vacuum energy outside the plates is therefore slightly higher than the vacuum energy inside the gap. This imbalance produces a force. The plates are pushed together, not because something is pulling them, but because empty space on one side behaves differently from empty space on the other. The force is small, but it is real. At separations of a few hundred nanometers, it becomes measurable with sensitive instruments. This is the Casimir effect, a force arising purely from the structure of the quantum vacuum. What makes this effect so important is not its size. It is not dramatic. It will not move furniture or bend steel beams. What matters is its origin. No particles are exchanged, no charges interact. The force emerges solely from how quantum fields behave in confined empty space. Geometry is the key. Change the shape, distance, or orientation of the boundaries, and the force changes predictably. The vacuum responds to structure. This immediately elevates emptiness from abstraction to physical participant. Empty space is no longer just a background condition. It has mechanical consequences. It pushes. The Casimir effect has been confirmed repeatedly in laboratory experiments using different materials, geometries, and techniques. Measurements agree with theoretical predictions to high precision. This is not a one-off curiosity. It is a robust phenomenon. There is something quietly decisive about this. Vacuum energy is no longer inferred indirectly through atomic shifts or theoretical necessity. It produces a force that can be measured between macroscopic objects. Empty space exerts pressure. This matters because it removes a lingering escape route. One could previously argue that vacuum fluctuations were mathematical artifacts, bookkeeping tools with no independent reality. The Casimir effect closes that door. The vacuum does work. It is also important to be clear about what this does and does not mean. The Casimir effect does not imply that the vacuum is unstable or explosive. The force is conservative. It does not generate energy from nothing. It depends entirely on configuration. Change the boundaries, and the effect adjusts accordingly. The vacuum is not a reservoir waiting to be tapped. It is a responsive system. There is a gentle elegance here. Emptiness does not shout to be noticed. It responds when constrained. It reveals itself when shaped. Two plates placed close together are enough to expose structure that would otherwise remain invisible. This reinforces a pattern that has appeared again and again. Space behaves differently when geometry changes. Curvature alters motion. Boundaries alter fields. Structure matters. The Casimir effect also provides a bridge between scales. It is observed in the laboratory, under controlled conditions using equipment built for precision. But the principles behind it do not belong only to the lab. They apply wherever quantum fields exist, which is everywhere. If geometry can alter vacuum behavior between metal plates, it can also alter vacuum behavior near stars, inside cavities, or across cosmological distances. The same rules apply. Only the scale changes. This is where emptiness begins to stretch beyond the experimental table. The vacuum is sensitive to shape and boundary. The universe is full of shape and boundary. Galaxies carve regions of space, horizons form, expansion stretches geometry itself. The Casimir effect does not explain these larger phenomena directly, but it establishes something essential. Vacuum energy is not speculative, it is not philosophical, it produces measurable forces. That fact alone changes the conversation. Empty space can no longer be described as nothing that happens to sit between objects. It reacts, it responds, it exerts influence when conditions demand it. There is also a subtle lesson about how physics advances. The Casimir effect was not discovered by looking for drama. It emerged from careful attention to constraints, symmetry, and consistency. The vacuum revealed itself not through spectacle, but through precision. In a sense, this is exactly how emptiness prefers to be known. By now, emptiness has acquired many roles. It carries geometry, it hosts fields, it stores energy, it fluctuates, and now it pushes. The laboratory confirmation of vacuum energy anchors decades of theoretical work in something tangible. It shows that the quiet restlessness of the quantum vacuum is not an abstract hum. It leaves fingerprints that instruments can detect. Once that is accepted, the question naturally expands. If vacuum energy exists here, between metal plates, then it exists everywhere. Not necessarily in the same form, not necessarily with the same effect, but as a property of space itself. The lab has shown that emptiness is active. The universe is much larger than any laboratory. And if empty space matters here, it may matter on the largest scales of all. By this stage, the idea of vacuum energy has become unavoidable. It is no longer a poetic phrase or a speculative suggestion. In modern physics, vacuum energy has a specific meaning. It refers to the energy associated with the lowest possible state of quantum fields, even when no particles are present. In quantum field theory, every field contributes to the vacuum. Each field has modes of vibration, and each mode carries a minimum amount of energy. Add together all of these contributions, across all fields and across all allowed modes, and the result is a non-zero energy associated with empty space itself. This is vacuum energy. It is important to be precise about what this does not mean. Vacuum energy is not energy stored in particles waiting to be released. It is not fuel. It is not something that can be extracted at will. It is a baseline property of the fields that make up physical reality. At small scales, vacuum energy reveals itself through effects like the Casimir force and subtle shifts in atomic behavior. At these scales, the theory and observation align well. The calculations are difficult, but they work. The difficulty arises when vacuum energy is considered at the largest possible scale. According to general relativity, energy has gravitational consequences. Energy affects the curvature of space-time. This applies not only to matter and radiation, but to any form of energy, including vacuum energy. If empty space carries energy, then that energy should influence the expansion of the universe. When physicists attempt to calculate the vacuum energy density using quantum field theory, they arrive at an answer that is extraordinarily large. Even conservative estimates produce a value that, if taken at face value, would cause space-time to curve violently. The universe would either collapse instantly or expand so rapidly that galaxies could never form. Yet this is not what is observed. Observations of the universe show that cosmic expansion is gentle on large scales. Galaxies form. Stars persist for billions of years. Space does not tear itself apart. Whatever vacuum energy exists, its gravitational effect is vastly smaller than naive quantum calculations suggest. This mismatch is known as the vacuum energy problem, sometimes called the cosmological constant problem. It is not a minor discrepancy. It is one of the largest known disagreements between theory and observation in all of physics. The problem can be stated simply. Quantum field theory predicts an enormous vacuum energy. Cosmological observations indicate a very small one. Both frameworks are exceptionally successful in their respective domains. Yet when they are combined, they clash. It is tempting to rush toward explanation. to suggest hidden cancellations, new particles, unknown symmetries, or exotic mechanisms. But restraint is important here. At present, there is no accepted solution. Physicists have explored many possibilities. Some approaches suggest that vacuum energy contributions cancel almost perfectly through mechanisms not yet fully understood. Others propose that only differences in vacuum energy matter gravitationally, not absolute values. Still others investigate whether gravity itself responds differently to vacuum energy than to other forms of energy. None of these ideas has yet achieved consensus. What matters for the present discussion is not how the problem will be solved, but what the problem implies. It implies that vacuum energy is real enough to demand explanation, yet subtle enough to evade straightforward interpretation. This tension tells us something important about emptiness. Empty space is not a blank slate where theory and observation naturally agree. It is a regime where the deepest principles of physics intersect and where those principles are not yet fully reconciled. There is also a lesson in scale. At laboratory distances, vacuum energy behaves exactly as quantum field theory predicts. At cosmological distances, its role becomes enigmatic. The same concept behaves differently depending on context. This does not mean one scale is wrong and the other is right. It means understanding emptiness requires frameworks that span an enormous range of sizes, from subatomic distances to the size of the observable universe. The vacuum energy problem is often described as embarrassing, but that word hides something more constructive. It highlights where understanding is incomplete. It marks the boundary between what is known and what is not. Importantly, the problem is not a failure of measurement. Astronomical observations are consistent and precise. Nor is it a failure of quantum mechanics at small scales. That framework continues to produce correct predictions. The difficulty lies in combining them. This reinforces a theme that has been developing throughout this discussion. Emptiness is not simple. It is not a leftover after everything else is removed. It is an active participant governed by rules that interact in subtle ways. Vacuum energy as a concept sits at the intersection of those rules. It links quantum fields to space-time curvature. It connects the smallest fluctuations to the larger structures. At present, physics does not yet know how to make all of these pieces fit together seamlessly. That uncertainty is not a flaw to be hidden. It is a fact to be acknowledged. There is also something calming about this admission. Nature is not required to be simple at every level. Understanding unfolds gradually. Some questions remain open, not because they are unanswerable, but because they are being asked at the edge of what current theories can handle. Vacuum energy, defined carefully and observed indirectly, is one of those edge concepts. It is real enough to matter, yet elusive enough to resist final explanation. This unresolved tension does not undermine the reality of vacuum energy. It deepens it. It shows that emptiness is woven into the structure of the universe in ways that are not yet fully transparent. As attention shifts outward, from laboratories to galaxies and beyond, the question becomes unavoidable. If vacuum energy exists everywhere, however small its effect may be locally, what role does it play in shaping the universe as a whole? That question belongs to cosmology, and it is there, on the largest scales imaginable, that emptiness takes on one more unexpected role. Once emptiness is allowed to carry energy, structure, and rules, the behavior of the universe at the largest scales begins to make more sense. Space itself is no longer a static container. It becomes something that can change. And one of the most important ways it changes is by expanding. Cosmic expansion is often misunderstood as objects moving through space, like fragments flying away from an explosion. That image is familiar, but it is misleading. The expansion of the universe is not primarily about galaxies racing through a fixed void. It is about space itself stretching. Distances increase not because galaxies are actively travelling outward, but because the space between them grows. Two galaxies can remain nearly at rest relative to their local surroundings, and still drift farther apart over time. The separation grows because the metric that defines distance is changing. This idea was not obvious when it was first discovered. In the early 20th century, astronomers were still debating whether distant nebulae were part of the Milky Way or separate galaxies entirely. Observations were limited, distances were uncertain. That changed through the work of Edwin Hubble. Using observations made at Mount Wilson Observatory in California, Hubble studied the light from distant galaxies and compared their apparent brightness with known stellar properties. He was able to estimate their distances and compare those distances to how their light was shifted toward longer wavelengths. What he found was remarkably simple. The farther away a galaxy was, the more its light was shifted. This shift indicated that distant galaxies were receding faster than nearby ones. The relationship was systematic and proportional. This was not random motion, it was a pattern. The conclusion was unavoidable. On large scales, the universe is expanding. What matters here is how that expansion is interpreted. The galaxies are not fleeing from a central point. There is no center to the expansion. Every region sees distant galaxies moving away, regardless of location. This is exactly what is expected if space itself is stretching uniformly. This stretching happens everywhere, including regions that appear empty. In fact, it happens most clearly in emptiness. Dense structures like galaxies and clusters are held together by gravity and internal forces. They resist expansion. The vast, sparsely populated regions between them do not. Cosmic voids, enormous regions containing very little matter, expand along with space itself. There is nothing in these regions pushing outward. There is simply nothing resisting the stretching. This is a crucial shift in perspective. Expansion does not require matter to move or act. It requires space to evolve. Even a region stripped of particles will grow in size as the universe expands. This behavior follows directly from general relativity. The equations governing space-time allow the geometry of space to change over time. Solutions to these equations describe expanding or contracting universes depending on the balance of energy and curvature. What Hubble observed was not the cause of expansion, but its effect. The expansion was already encoded in the structure of space-time. Galaxies merely revealed it by drifting apart. Scale matters enormously here. On small scales, expansion is negligible. The distance between atoms in a table does not grow. The solar system does not expand. Even galaxies remain bound. Local forces dominate. On larger scales, gravity still shapes structure, but it does not prevent expansion entirely. Galaxy clusters form and persist, yet clusters themselves drift apart over time. Beyond that, on the largest scales of all, expansion dominates. This scale dependence is why expansion can coexist with stability. The universe can expand while still allowing stars, planets, and people to exist. Expansion is not a tearing force. It is a gradual stretching that becomes significant only over immense distances. It is also why emptiness plays such a central role. Most of the volume of the universe is not filled with matter. It is filled with vast regions of low density. These regions faithfully track the expansion of space itself. In that sense, emptiness reveals the universe's behavior more honestly than matter does. Matter resists, distorts, and complicates. Empty space stretches freely. This does not mean that expansion originates from emptiness alone. The rate of expansion depends on the total energy content of the universe, including matter, radiation, and whatever else contributes to space-time curvature. But emptiness provides the stage on which expansion becomes visible. There is a gentle conceptual shift here. Instead of imagining expansion as something happening to objects, it becomes something happening to space. Distance itself evolves. This idea can feel abstract, but it has direct observational consequences. Light travelling through expanding space is stretched along with it. Its wavelength increases. This is why distant galaxies appear redshifted. The light has not lost energy through friction or resistance. The space it travelled through has changed. Even the most empty regions participate. A photon crossing a cosmic void experiences the same stretching as one crossing a region filled with matter. Emptiness does not shield space from its own evolution. By now, empty space has accumulated a remarkable list of responsibilities. It carries geometry, it hosts fields, it stores energy, it fluctuates, it pushes between plates, and it stretches slowly and steadily on the largest scales imaginable. What remains is a final and surprising twist. For much of the 20th century, scientists expected expansion to slow over time. Gravity, they reasoned, should gradually pull everything back together. Observations would soon reveal otherwise. The expansion of the universe is not merely continuing, it is speeding up, and that discovery will force emptiness to take on one more role, one that reshapes the future of the cosmos itself. For much of the 20th century, there was a quiet expectation guiding cosmology. The universe was expanding, but gravity should be slowing it down. Matter attracts matter. Over time, that attraction ought to act like a brake, gradually reducing the rate of expansion. Whether the universe would eventually collapse, coast forever, or settle into some balance remained open, but deceleration felt natural. That expectation was reasonable. It followed directly from general relativity, and from the known behaviour of matter and energy. Expansion required explanation, but slowing expansion felt inevitable. Then observations began to say otherwise. In the late 1990s, 2 independent research efforts set out to measure the expansion history of the universe with greater precision than ever before. These efforts were known as the Supernova Cosmology Project and the High Z Supernova Search Team. Their focus was on a particular kind of stellar explosion called a Type 1a supernova. Type 1a supernovae are valuable because they behave in a remarkably consistent way. When a white dwarf star reaches a critical mass and explodes, the brightness of the explosion follows a predictable pattern. This makes such supernovae reliable cosmic distance markers. By comparing how bright they appear with how bright they are known to be, astronomers can determine how far away they are. These teams observed supernovae in distant galaxies, looking back billions of years into cosmic history. They measured both distance and redshift, allowing them to reconstruct how fast the universe was expanding at different times. The expectation was clear. Distant supernovae should appear brighter than they would in a steadily expanding universe, reflecting a past when expansion was faster and had since slowed. They did not. Instead, the supernovae appeared dimmer than expected. The implication was startling. The expansion of the universe had not been slowing down. It had been speeding up. This was not a subtle effect buried in noise. It was consistent across observations. 2 independent teams using different methods and analyses arrived at the same conclusion. The universe's expansion is accelerating. This discovery reshaped cosmology almost overnight. An accelerating expansion requires something that counteracts gravity on the larger scales, something that does not clump like matter, something that exerts a kind of repulsive influence as space expands. This something became known as dark energy. The name is intentionally modest. Dark energy does not imply a specific substance or mechanism. It is a label for a set of observed effects. It describes whatever is causing the expansion of the universe to accelerate. What makes dark energy especially relevant to emptiness is where it appears to reside. Observations indicate that dark energy is not concentrated in galaxies or clusters. It does not pool in dense regions. Instead, its influence seems uniform across space. It behaves as a property of space itself. As the universe expands, the total amount of dark energy increases, not because more is being created, but because there is more space for it to inhabit. The energy density remains roughly constant even as space grows. This is profoundly counterintuitive. Matter becomes more dilute as space expands. Radiation thins out, but dark energy does not fade. It persists. This persistence suggests that dark energy is tied to the vacuum of space, to emptiness itself. It is important to emphasize what is known here and what is not. The accelerating expansion is observed. The influence of dark energy is inferred from multiple independent measurements, including supernovae, cosmic microwave background observations, and large-scale structure surveys. These observations are consistent. What dark energy is remains uncertain. There are theoretical interpretations. One possibility is that dark energy corresponds to a cosmological constant, a term originally introduced by Albert Einstein into his equations of general relativity. In this view, empty space has an intrinsic energy density that causes it to expand. Another possibility involves dynamic fields that change slowly over time. Other ideas explore modifications of gravity on cosmic scales. None of these explanations has been confirmed. What matters is that explanation has not outrun observation. The data come first. The universe is accelerating. Any acceptable theory must account for that fact. This discipline is essential. It keeps speculation grounded. Dark energy is not a placeholder for imagination. It is a response to measurement. The role of emptiness in this picture is striking. The vast majority of the universe's volume is empty space. Galaxies and clusters occupy only a tiny fraction. If dark energy is a property of space itself, then emptiness dominates the universe's behavior. On the larger scales, matter becomes secondary. It shapes structure locally, but it does not control the overall expansion. Empty space does. This reverses a long-held intuition. Historically, emptiness was treated as absence, as what remained when everything else was removed. In the modern cosmological picture, emptiness becomes the main actor. This does not mean matter is unimportant. Stars still shine, galaxies still form, chemistry still operates. But the long-term fate of the universe is governed by how space itself behaves. There is a calm audacity to this conclusion. Without drama or spectacle, empty space quietly takes control of cosmic evolution. The acceleration is gentle. It does not tear galaxies apart. It does not disrupt bound systems. It becomes noticeable only across immense distances and over billions of years. The universe does not explode outward. It stretches faster and faster, patiently. This gentleness is important. Dark energy does not behave like a violent force. It does not push objects apart locally. It changes the rate at which space expands globally. That distinction preserves the stability of the universe while reshaping its future. It also deepens the connection between emptiness and energy. The same vacuum that produces subtle forces between metal plates now appears to shape the expansion of the cosmos. The same concept spans laboratory experiments and astronomical observations. This does not mean the two are identical in mechanism. Caution is required. But the conceptual link is unavoidable. Energy associated with empty space has consequences at every scale. There is temptation to treat dark energy as mysterious in a dramatic sense. In practice, its mystery is quiet. It reveals itself through careful measurement, patient analysis, and consistent patterns. The acceleration of the universe was not discovered by looking for something strange. It was discovered by noticing that something expected did not happen. That absence of deceleration mattered. Once again, emptiness reveals itself not by shouting, but by refusing to behave as expected. At this stage, emptiness is no longer a background assumption. It is the dominant component of the universe's energy budget. It shapes the past, the present, and the future of cosmic expansion. The universe is not being driven apart by matter flinging itself outward. It is being carried along by the properties of space itself. Empty space, once thought to be nothing at all, now appears to be the quiet engine of cosmic history. And that realization forces one final reassessment. If emptiness dominates the universe's behavior, then understanding emptiness is not a side question. It is the central one. At this point, a question almost asks itself, if empty space carries energy, and if that energy appears to drive the accelerating expansion of the universe, then are vacuum energy and dark energy the same thing? The short answer is that they might be related. The careful answer is that they are not yet known to be the same, and that difference matters. Vacuum energy and dark energy share several striking similarities. Both are associated with empty space rather than with matter or radiation. Both appear to have roughly uniform effects across the universe. Both resist dilution as space expands, and both influence the geometry of space-time itself. These overlaps make the identification tempting. In fact, one of the simplest theoretical explanations for dark energy is that it is vacuum energy acting on cosmic scales. In this view, the energy associated with the quantum vacuum naturally appears in Einstein's equations as a cosmological constant, producing accelerated expansion. This idea has an appealing elegance. It connects laboratory-scale physics to cosmology. It suggests that the same vacuum responsible for subtle forces between metal plates also shapes the fate of the universe. But elegance is not evidence. There are also deep problems with this identification. The most serious is magnitude. When physicists calculate vacuum energy using quantum field theory, they obtain values that are enormously larger than what cosmological observations allow. Even when estimates are made conservatively, the predicted energy density of the vacuum exceeds the observed value associated with dark energy by an extraordinary amount. This discrepancy is not small. It is not a factor of 2 or 10. It is many orders of magnitude. The precise number depends on how the calculation is framed, but the mismatch is among the largest known in physics. This alone prevents a clean equivalence. If vacuum energy and dark energy are the same thing, then something must suppress the gravitational effect of vacuum energy almost perfectly, leaving only a tiny residue. No agreed mechanism for this suppression currently exists. There are also conceptual differences. Vacuum energy arises naturally within quantum field theory as a baseline property of fields. Dark energy, by contrast, is inferred from astronomical observation. It is defined operationally by how it affects expansion, not by a microscopic description. In some models, dark energy behaves exactly like a cosmological constant, with constant energy density over time. In others, it may vary slowly. Observations so far are consistent with a constant value, but they do not yet rule out subtle evolution. Vacuum energy, as usually calculated, is static. It does not change with time. This similarity supports the connection, but it does not prove it. Another complication is that gravity may respond differently to vacuum energy than to other forms of energy. General relativity treats all energy as equivalent in its effect on space-time curvature, but this assumption has not been tested directly for vacuum energy. It remains possible, though unproven, that vacuum energy gravitates in an unusual way. Because of these uncertainties, physicists are careful with language. Dark energy is not defined as vacuum energy. It is defined as whatever is causing the observed acceleration. Vacuum energy is one candidate explanation among several. This caution is not hesitation for its own sake. It reflects experience. Many ideas that seem obvious at first glance turn out to be incomplete when examined closely. There is also an important methodological point. Physics progresses by separating what is observed from how it is interpreted. The accelerating expansion is observed. The existence of dark energy as a description of that observation is well supported. The identification of dark energy with vacuum energy is an interpretation, not a measurement. At present, that interpretation remains provisional. This does not mean the connection is unlikely. Many physicists consider vacuum energy the most natural explanation available. It fits comfortably within existing frameworks. It requires no new entities beyond those already present in quantum field theory and general relativity. But natural does not mean correct. The history of physics is full of ideas that felt inevitable until they were replaced. Absolute space once seemed unavoidable. The ether once seemed necessary. Each was elegant. Each was wrong. This perspective encourages restraint. The overlap between vacuum energy and dark energy is suggestive, not decisive. The differences are unresolved, not dismissed. It is also worth noting that the difficulty here may signal something deeper. The vacuum energy problem highlights the tension between quantum mechanics and gravity. These two pillars of modern physics work extraordinarily well in their respective domains, yet they do not fit together cleanly. Dark energy sits precisely at that intersection. In this sense, the question of equivalence may be premature. It may be that neither vacuum energy nor dark energy is fully understood in isolation, let alone in combination. The correct framework may require concepts that do not yet exist. This does not undermine what has already been learned, it sharpens it. Emptiness has proven itself to be structured, energetic, and influential. It has reshaped gravity, driven expansion, and resisted simplification. What remains uncertain is not whether emptiness matters, but how. There is a calm honesty in leaving this question open. Physics does not require every mystery to be resolved before progress continues. It requires clarity about what is known, what is inferred, and what remains unknown. At present, vacuum energy and dark energy occupy overlapping conceptual territory without complete identification. They may be two descriptions of the same underlying phenomenon viewed from different scales, or they may be related but distinct, connected by mechanisms not yet understood. What can be said with confidence is that empty space is not inert. Whatever its precise role, it participates in the universe's evolution in measurable ways. The temptation to declare a final answer is understandable, but restraint preserves accuracy. The absence of resolution is not a failure. It is a marker of where understanding currently ends. As attention turns toward those limits, the question of emptiness becomes less about what space is doing, and more about what current theories can and cannot explain. The quiet influence of empty space has carried physics this far. What lies beyond remains an open boundary. At this point, it becomes important to slow down and acknowledge the edges of knowledge. Physics has uncovered a great deal about empty space, but it has not uncovered everything. Some questions remain unanswered not because they are uninteresting, but because they sit beyond what current methods can reliably reach. One of the central challenges is observational. Emptiness does not emit light. It does not announce itself directly. Its presence is inferred through effects, influences, and constraints. Curvature reveals itself through motion. Vacuum fluctuations reveal themselves through shifts and forces. Dark energy reveals itself through expansion. In every case, emptiness is detected indirectly. This indirectness imposes limits. Measurements depend on interpreting signals that pass through complex systems. Astronomical observations, for example, rely on light that has travelled for billions of years, influenced by matter, gravity, and expansion along the way. Extracting the contribution of empty space alone requires careful modelling and assumptions. Even in laboratories probing the vacuum pushes technology to its limits. Effects like the Casimir force are tiny and require extreme precision. Background noise, material imperfections, and thermal effects must be controlled. These experiments confirm that the vacuum has structure, but they do not reveal its full complexity. There are also theoretical limits. Quantum field theory works extraordinarily well for predicting interactions at accessible energies. General relativity works extraordinarily well for describing spacetime on large scales. But when emptiness is examined at the intersection of these frameworks, tensions appear. One example is the behaviour of spacetime at extremely small scales. Near what is known as the Planck scale, roughly 35 orders of magnitude smaller than everyday lengths, current theories lose predictive power. Quantum fluctuations of spacetime itself may become significant, but no complete theory yet describes them. This is not a failure of effort, it is a recognition of boundary. Without experimental access to such scales, theory alone cannot be confirmed. Speculation without measurement remains speculation. There are also limits imposed by the universe itself. The observable universe is finite in age and extent. Light has travelled only so far since the beginning of cosmic expansion. Regions beyond that horizon cannot be observed directly. Whatever emptiness does beyond that boundary remains unknown. Even within the observable universe, certain questions resist clean answers. Does vacuum energy change over time? Does dark energy remain constant forever? Does space-time itself have a smallest meaningful scale? These questions can be framed mathematically, but they cannot yet be settled empirically. This uncertainty is not something physics tries to hide. In fact, it is treated with care. Honest science distinguishes between what is measured, what is inferred, and what is hypothesized. Confusing these categories creates false confidence. Restraint plays a crucial role here. The temptation to explain emptiness completely is strong, especially given how central it has become. But explanation must follow evidence, not precede it. History offers a clear lesson. Concepts once treated as final truths were later revised or replaced. Absolute space, the ether, and classical emptiness all seemed complete until new evidence reshaped them. Recognizing limits protects against repeating that mistake. There is also a practical reason for caution. Emptiness operates across enormous ranges of scale. What appears smooth and calm at one scale may behave differently at another. Extrapolating without constraint risks error. This does not mean progress has stalled. On the contrary, the boundaries of understanding are often the most productive regions of inquiry. They guide new experiments, motivate new theories, and sharpen questions. What matters is maintaining clarity about what is known. Empty space carries geometry. It hosts fields. It fluctuates. It influences expansion. These are supported by evidence. How these features emerge from a deeper framework remains open. There is a quiet discipline in accepting this. Science does not promise completeness at every moment. It promises reliability within stated limits. In this sense, uncertainty is not a weakness. It is a feature of honest inquiry. It marks the frontier where understanding is still forming. By acknowledging what cannot yet be measured, physics preserves its credibility. It avoids overreach. It allows future discoveries to reshape the picture without contradiction. As the discussion of emptiness draws together, these limits serve an important purpose. They prevent the story from becoming a closed loop. They leave room for refinement. What has emerged so far is not a final answer to the question of emptiness, but a layered understanding. Emptiness is not nothing. It is structured, energetic, and influential. Yet it is not fully mapped. The remaining uncertainty does not erase what has been learned. It frames it. And with that frame in place, it becomes possible to step back and see the larger picture, to gather what is known without pretending to know what is not. The quiet boundaries of measurement are not an ending. They are the context in which understanding remains honest. From here, the task is not to fill every gap, but to integrate what has been revealed into a coherent whole. That synthesis does not resolve every mystery. It clarifies where mystery truly remains, and that clarity is its own form of understanding. The question can now be asked again, with far more care than when it first appeared. Is empty space really empty? At first glance, the answer seems to depend on what is meant by empty. In everyday language, empty means absence. No objects, no motion, no substance. That definition works well for daily life. But physics has shown that it is not precise enough to survive close inspection. In classical mechanics, empty space was treated as a passive background. Remove matter, and what remained was an inert stage on which motion unfolded. That picture was enormously successful. It allowed Isaac Newton to describe planetary motion with remarkable accuracy. It still underpins much of engineering and practical calculation today. Within that framework, emptiness could be treated as nothing of consequence. It did not resist motion. It did not store energy. It did not influence outcomes. For many purposes, this remains a useful approximation. Relativity changed that picture. Special relativity united space and time into space-time, revealing that even in the absence of matter, the structure of space imposes limits. Distances and durations depend on motion. The speed of light acts as a universal constraint enforced by space-time itself. General relativity went further. It showed that space-time can curve, ripple, and evolve. Gravity is not a force acting through space, but a feature of space itself. Empty regions can carry curvature. Gravitational waves can pass through matterless regions. Time can flow differently depending on position, even in areas stripped of particles. At this stage, emptiness is no longer inert. It has geometry. It shapes motion. Quantum physics reshaped emptiness again. Quantum mechanics forbids perfect stillness. The uncertainty principle ensures that no system can reach a state of absolute rest. Even the lowest energy state carries residual motion. Quantum field theory made this unavoidable. Fields exist everywhere space-time allows them to exist. Particles are excitations of those fields, not fundamental occupants. Removing particles does not remove the fields. Their ground states remain, and those ground states fluctuate. This is the quantum vacuum, not a void, but the calmest state allowed by the rules of the theory. Calm, but not silent. Vacuum fluctuations are constrained, local, and fleeting. They do not produce chaos. They do not violate conservation laws, but they influence measurable quantities. They shift energy levels. They alter forces. They produce effects like the Casimir force, which has been confirmed in laboratories. On the larger scales, emptiness plays an even more surprising role. The expansion of the universe is not driven by matter flying outward, but by space itself stretching. That stretching occurs most freely in regions with very little matter. Observations show that this expansion is accelerating. Whatever causes that acceleration behaves as a property of space. Dark energy, as it is called, dominates the universe's energy budget. It does not clump. It does not dilute. It persists as space grows. This brings emptiness from the margins to the center. Empty space is not a backdrop. It is the dominant influence shaping the universe's future, and yet important uncertainties remain. The relationship between vacuum energy and dark energy is not fully understood. Calculations and observations disagree by enormous amounts. The behavior of space-time at the smallest scales is unknown. The limits of current theories are clearly visible. This means there is no single, final answer to the question of emptiness. The answer depends on context and scale. At human scales, empty space behaves as if it is empty. A room cleared of objects feels empty because the effects that remain are too subtle to notice. At engineering scales, treating space as inert works perfectly well. At atomic scales, emptiness becomes structured by fields and quantum rules. At cosmological scales, emptiness governs expansion and fate. Each description is accurate within its domain. None is complete on its own. There is a quiet lesson in this. Physics does not replace one simple picture with another. It layers them. Older models are not discarded. They are refined, limited, and placed in context. Emptiness, once imagined as nothing, has become one of the most active concepts in science. It carries geometry, energy, fluctuation, and influence. But it does so without drama, without noise, without obvious presence. It reveals itself only when carefully examined. What is known is substantial. Empty space is not nothing. It is structured. It participates in physical law. It shapes motion, time, and expansion. What remains unknown is equally important: how quantum fields and gravity fully combine, why vacuum energy appears so small cosmologically, what emptiness looks like at the deepest level. These are not failures, they are frontiers. So is empty space really empty? In the simplest everyday sense, yes. In the physical sense revealed by centuries of careful work, no. Empty space is calm, but not void. Silent, but not inactive. Simple in appearance, and endlessly layered beneath. Understanding that difference does not require alarm or wonder, it requires patience, and perhaps a willingness to let nothing be more than it first appears. The journey through emptiness ends not with a revelation, but with a steadying perspective. What once seemed like a simple absence has revealed itself as something layered, structured, and quietly active. Empty space, examined carefully and patiently, turns out not to be a void at all, but a participant in the workings of the universe. At the most familiar level, emptiness still behaves as expected. A room without objects feels empty. A stretch of sky between stars appears dark and still. For everyday purposes, treating space as nothing in particular works perfectly well. Classical physics relies on this approximation, and it remains enormously useful. Much of engineering, navigation, and daily technology would not function without it. But physics has shown that this simplicity is conditional. Space is not merely a container. Relativity revealed that space and time form a unified structure, space-time, with measurable geometry. Even when stripped of matter, space-time retains form. It limits speed. It shapes motion. It bends and stretches in response to energy and mass. And those deformations persist even in regions that appear empty. Quantum physics adds another layer. Perfect stillness is forbidden. Fields exist everywhere space-time allows them to exist, and those fields cannot be completely quiet. Their lowest energy states fluctuate gently, constrained but unavoidable. Removing particles does not remove activity. It reveals the background hum beneath it. This hum is not chaotic. It does not threaten stability. It does not erupt into noise. It remains disciplined, bounded by the rules of quantum mechanics. Its effects are subtle, but real. They can be measured, predicted, and confirmed. Laboratory experiments demonstrate this clearly. The Casimir effect shows that empty space responds to geometry. When boundaries change, the vacuum adjusts, producing measurable forces. Emptiness pushes back, not dramatically but decisively. On the largest scales, emptiness takes on a role that would have once seemed unimaginable. Space itself expands. That expansion does not require matter to move or act. It happens most freely where matter is absent. Observations show that this expansion is accelerating, driven by something that behaves as a property of space itself. Dark energy, whatever its ultimate nature, makes one thing clear. The behavior of the universe is dominated not by what fills space, but by space itself. Emptiness governs the long-term evolution of the cosmos. This does not mean that emptiness is fully understood. Important questions remain open. The relationship between vacuum energy and dark energy is unresolved. The behavior of space-time at the smallest scales is unknown. Current theories, while powerful, do not yet form a complete picture. But uncertainty here is not unsettling. It is expected. It marks the boundary between established knowledge and ongoing inquiry. What has been learned is substantial. Empty space has structure. It carries geometry. It hosts fields. It contains energy. It fluctuates. It influences motion, time, and expansion. These are not speculative ideas. They are supported by observation, experiment, and theory working together. At the same time, emptiness is not loud. It does not announce itself. It does not demand attention. It behaves consistently and calmly, revealing its properties only under careful examination. Its influence is gentle, cumulative, and patient. There is something reassuring in this. The universe does not rely on hidden chaos or dramatic forces lurking in nothingness. It relies on quiet rules applied everywhere, even where nothing seems to be. The idea of absolute nothingness, while compelling philosophically, finds little support in physical reality.